Okay, for the first law, which is Coulombs law, let's see, just review the picture we have. We have charge Q1 to charge Q2, the vector R12 between the charges. Refined experimentation with things a lot more spherically symmetric than pieces of tape, where we can actually measure the interaction in a way that we have confidence in. We end up with the law that the force exerted by charge 1 on charge 2, and that would be a force that we could designate F12, is equal to, is proportional to the product of the two charges, and that product could be positive or negative, divided by R12 squared, the magnitude of this vector, the square of the magnitude of this vector, multiplied by a unit vector in the direction of R12. So that gets the force in the right direction. Q1 times Q2 is negative if the forces are unlike, which would give you a force back in this direction. And if the charges are like, the force is in the same direction as R12. The constant K, and we're reviewing here, we know that that constant is 9 times 10 to the 9th Newton meter squared per Coulomb squared, good to about 3 significant figures, allows us to calculate the force of any charge on any other charge. Electric field is going to be defined as the electric field of a single charge. Well, electric field in general is the force per unit of test charge inserted at a point within the field. Now, the field of a single charge, Q, at some position, is then going to be, we regard the charge Q as, let's say, Q1, and then we have a charge capital Q replacing Q2, Q test, a test charge. If we calculate the force on a test charge due to the charge Q at a point, then we divide that force by the test charge. What are we left with? We're left with just K times little q over R squared times the unit vector, R vector, divided by its magnitude. And that'll be the electric field due to the charge Q at some position. And of course, the R vector is the vector that goes from the position of the charge to the position at which we're calculating the field. Again, with this is a synopsis. We've been through the details, and we're going to be expanding on them a little bit. We just want to get the basic idea. And then the idea that the total electric field is the sum of the electric fields of individual charges. So if we have a distribution of charges, we just add the electric fields that we get from each charge to get the electric field at a point. And that's the principle of superposition. The units of these quantities, the units of the electric field are newtons per coulomb. Newtons for force, coulombs for the charge. The other definition that's relevant here is that voltage is electric field times distance. That is, if you have a constant electric field and 2 points separated by distance d in that electric field, the voltage, the potential difference between the points, is E times d. The units of E being newtons per coulombs, the units of d being meters. The units of this potential difference are joules per coulomb, the amount of energy per coulomb of charge, interpreted as the energy per coulomb of charge required to move the charge over this distance d. And if the field isn't constant, then this is defined as a simple line integral. I haven't included that definition here. The units then are joules per coulomb, and we call those volts. Okay, so joule per coulomb is a volt. And the units are really very useful and important here. If you can reason things out in terms of the units, you get closer to the meanings of the various quantities, and you expand your ability to reason your way through different situations. Now, having defined a volt as a joule per coulomb, then it's pretty clear that a joule being a Newton meter, if we divide that by a meter, we get a Newton. So if we divide this volt or joule per coulomb by meters, we get newtons per coulomb, which means that newtons per coulomb could also be expressed as volts per meter. Two different ways to think of the meaning of the electric field.